Hi, my name is Yuri Zuban. I'm a conversational backend developer at Master of Code Global and Glia. And in this video, we'll take a look at three setups for semantic search. Each of them will be using OpenAI embeddings for generating vector representations of the text, but different vector stores. Namely, we will compare Pinecone, FAISS, and pgvector. We will go through three Colab notebooks, which implement the integration with the corresponding vector database, and then I will subjectively characterize each of the three setups by its efficiency, effort needed to implement it, and the cost. This comparison is a byproduct of my other project, which I called Dry, or Do Not Repeat Yourself. Dry is intended to be a feature for group chatbots, for Telegram or other messengers, and the problem which it solves is that people tend to ask the same things multiple times, and this may look like sort of spam. So I thought that it might be nice to create a chatbot which would take each incoming message and search for similar previous messages in the background. And if such messages are found, it would write that, hey friend, this question has been asked before, and here are those previous examples. Looks like semantic search might be the way to solve this problem. And the overall schema of this project will be the following. So for each incoming message, a dense vector will be generated using an embeddings model. And this vector will be used to search in the vector database for similar messages, and if such messages are found, they will be returned into the chat. At the same time, using the same embeddings vector, the original message and some other metadata will be stored in the database and will be available for searching when the next message is received. So before we look into specific Google Colabs, let's quickly and in general terms remind what is semantic search in context of large language models and vector databases. So there exist embeddings models, and in this project I was using the model from OpenAI called Text Embeddings ADA 002. These models were trained on different combinations of words, and they allow to generate a so-called vector or embeddings vector or dense vector for a given string. And by a string we mean a word or a sentence or a paragraph. That is some sequence of tokens. Tokens are parts of words. So, and for each string, this model allows to generate this vector, which is a big sequence of floating numbers, which shows where in the multi-dimensional space of this model each specific string is located. So, and if to speak about this specific pet project, let's say that first we get some message about how get to the museum. We generate a vector and we store it into this database, let's say somewhere here. And this was a string, how to get to the museum. Then sometime later another question comes, which is, hi, could you please tell how to come to find a museum? And though this different question contains a bit different words, it has a similar meaning, and the model will return a vector which will locate the string somewhere close to the previous one. And let's say then we get yet another request. For example, I'm looking for a museum called something, and again it will be located somewhere here. And using this similarity search, we can retrieve phrases with similar meaning. So let's say this will be a museum requests. And in this similar manner, we may have some other requests like currency exchange requests and so on. Let's look into our Google Colabs. And the first one we will take a look will be an integration with Pinecone. So Pinecone is a fully managed vector database. It's easy to use and quick to integrate, however it is paid. But it has a free tier as well. Here is my account in Pinecone, and at the moment there is no project here. I will create some project. Let's call it dry. It will be using a free tier hosted on Google Cloud, and let's say I will choose this one, the environment US West 1 GCP 3, and that's it. And I will click create a project. It will take some time to initialize. While it is starting, let's look at this code. So first, we need some environment variables to be set. That is OpenAI API key and organization name, Pinecone environment, which in our case will be this one. So let's create a new file, call it env, and here this environment will be US West 1 GCP 3. Index name will be, let's say, dry. Similarity search limit will be 0.9. Pinecone returns similar score from 0 to 1, and the higher the value, the closer by meaning the given string is to those strings found in the database. Top K is defines how many records to return at maximum. So I will also set these values, and here is where we get the API key for Pinecone. We've got our project, and our index will be created programmatically. Let's run this cell. Just to confirm that the environment variables were set, we will print out the value for Pinecone index name. The next cell will install a number of the needed packages: TikToken, OpenAI, Pinecone client. Then we will initialize the OpenAI client and Pinecone client. So let's run it. To confirm that we are able to interact with OpenAI API, we will print a list of OpenAI models, and also to check if we can send requests to Pinecone, we will list Pinecone indexes, but we expect to get none of them. So this is the list of OpenAI models, and here is the list of Pinecone indexes. And if we do not have an index yet, we will create it. So if Pinecone index, in our case dry, is not in the list, we will create this index, and we will set its dimensionality equal to the number of dimensions of this model, which is 1536. Again, creation of the index takes some time. Okay, so we've finally got our index called dry. Let's check what is here, and we see that it contains 0 vectors at the moment. We connected to our index, and we are able to save something there. This will be our test messages. So we have 3 objects. Each has a key text with some value, actually in Ukrainian, in a non-major language, and some metadata like author, date, and URL. Next, we have a number of functions we will be using. The first one is to generate an embeddings vector. It will make a request to the OpenAI API and use this string and the given embeddings model, and will return that array of embeddings. Then we will have a function to generate a vector ID, and the vector ID will be the timestamp plus this message name, message ID. And save vector plus meta function will take the vector and the object of the message, which is called meter, and it will assert this value to this combined information into the database. And now for these three messages, for each message in text messages, we will generate an embeddings vector and save this vector to the database. So we see the logs saying that generated embeddings for some string, the vector ID, and the vector was inserted to the database. And these logs are written 3 times. If we go to the console, we'll immediately see that there are 3 vectors here. And if we take a vector ID, we are able to search for some vector. So I entered the vector ID, click fetch, and here we see that the vector which has ID such and such, here we see the value for those floating point numbers, and then metadata contains author, date, text, and URL. That is that full message object. Next, we have this function called getTopRelevantMessages, which takes some text or message, it generates a vector, and then it searches against the Pinecone vector database using this vector and also the number of messages to return, and this flag indicates that we need the metadata to be returned. And then this function filters those returned messages by the score. So we need only the messages with relevance score higher or equal to relevance limit, and in our case it is 0.9. So let's confirm that we set the correct values, and then we have some testing messages, let's say 3 test messages. And let's check how our similarity search works. So if we run this message get top relevant messages, we see the following logs. So it generated the vector, and then it shows that it got 3 matches in general. They are ordered by their score, and the top one has the score 0.92. And relevant matches is the messages which we get after filtering by that relevance score. That is this first message, which says where to exchange currency in Ljubljana. It got 1 match, and it is the message which in Ukrainian says that good evening, where in Ljubljana or Novo Mesto can I exchange currency into euro, not dollars, please. So, and here we have also this vector printed out. We can check the similarity search for other 2 test messages. And in this case, we see that though 3 messages were returned, even the top one has the score lower than our threshold limit. That is, no relevant matches were found. And in this third case, again, the message with highest score is not relevant enough to be returned. Okay, then next we have a function called getSimilar and this function will both look for similar messages and store the current message with its embeddings vector into the database. And finally, I have a bigger list of messages for which we will generate message objects, and then we want to test all of them with our logic. Let me add one console log for better visibility. So let's say if we matched something, let's print that it's a match. So, and we see the output, and some messages have relevant matches. So, and here we see that already got almost 100 vectors. And let me sum up my impression from Pinecone. It does its job. So for efficiency, I will give it 3 stars. It was easy to integrate Pinecone. There are good examples for Python and for TypeScript. So here the effort was low. Also, as this is a managed service, we do not need to bother about hosting and scaling and support and so on. So here we can give 1 star. The effort to integrate is quite low. Pinecone is a managed service. It has a free plan which should be enough for a pet project. However, for a commercial project one would need to buy some paid plan. And let's say that we expect our service to have 50k daily users, and they will be generating around 50k messages daily, and this will mean that we will create and store 50k vectors daily, or 1.5 million vectors monthly. If we look at pricing, for example, here's a standard plan for $70 a month, and it should be enough for storing around 5 million vectors. So looks like we could try with this first plan, and $70 a month should be enough for start. So let's mark this cost as relevantly high. Okay, let's proceed to our second vector database, and this is FAISS. As the documentation says, FAISS is a library for efficient similarity search and clustering of dense vectors. I got acquainted with it, learning to work with LangChain. FAISS is an in-memory database and should be quite efficient and quick. However, it has some nuances, and for example, one of them is that if your index becomes really big, you need to think how to store it and how to share it locally, possibly among several machines. Another thing is that FAISS out of the box is not intended for storing any metadata, like raw messages or links or something else. So if you need such info, you will have to store and manage that information in a separate database and link with vectors stored in FAISS somehow. And this is actually why I used not FAISS out of the box, but I used LangChain's wrapper for FAISS, which has this thing solved. That is, it allows to store metadata together with vectors. Let's go through this Google Colab, which shows an example of integrating with FAISS. And first we need to set some environment variables. For that we will create an env file, and we need to store the following variables there. Let's call our FAISS index dry. In case of FAISS and also pgvector, the lower the value of the score, the more close or similar by their meaning phrases are, which is opposite to what we've seen for Pinecone. So we will have similarity search limit, let's say 0.15. Top 5, we will be returning maximum 5 matches. And we also need to set OpenAI key, OpenAI API key, and OpenAI organization name. We set our environment variables. Let's run this cell, and we confirm that we've got the value of FAISS index name. Here we have a cell which allows to mount our Google Drive, where we possibly may have a FAISS index created previously. However, now we will create it from scratch. Here we have several test messages, like 3 objects, which have keys text, author, date, and URL. Next, we will install OpenAI and configure the OpenAI client. To confirm that we are able to interact with the OpenAI API, we will list the models. Next cell, we will install the dependencies needed to work with FAISS, namely FAISS CPU, LangChain, and tick token. We will be using the CPU version of FAISS. There is also a GPU one. Next, we will initialize our index. We will use some test input, and this line, FAISS from documents, will initialize the index and save the first record there using the given embeddings model. So next we have several functions which will be used in our project. These are similar to those which we've seen for Pinecone. The first one is for generating vectors. The next one, function getVectorID, for creating IDs for our vectors by joining the timestamp and message ID. The next function, saveVector plus meta, it will be saving our embeddings to the FAISS index together with the document. So we will be using the add embeddings function from a LangChain. And in this cell, we will use our 3 test messages to test how we save those to the vector database. We see that a vector was generated for a given message. The vector ID is this one, and each vector was added to the database. It is possible to save the index locally. For example, if we run this cell, we will get a folder here which contains the index, which can be backed up, and for example it can be copied to our shared Google Drive for using later. However, now we will not do that. And here this cell shows how to mount the existing index. Next we have the function called getTopRelevantMessages, and it will be using the function from LangChain called similarity search with score by vector. This function will be taking an embeddings vector and searching for similar vectors in our index. And then it will print all the found records and will filter for most relevant ones using the relevance limit, which we set as an environment variable. So let's test how our similarity search works. We will run this get top relevant messages function using the first message and the vector generated for it. And here we see that there were 4 matches. However, the top one did not reach the relevance score limit. And in this case, as the message for which we were looking for some similar phrases was exactly or almost exactly the same as the one already stored in the database, so the match was quite high, almost 0. Next, we have a function called getSimilar and store. What it does, it generates vectors, a vector, and then it searches for relevant messages using the function we just tested, and then it also saves this new message together with the vector to the index. And again, as with Pinecone, we have this long list of messages which I've copied from some random chat. And for each message, we will generate the message like message objects for each message, and then we will run that getSimilar and store function looking for similar phrases. For better analysis, let's add some log here. That is, if we found some relevant match, let's print that it's a match. And let's run our cycle. And we see that for some phrases, some suggestions were found. How would I characterize my first impression from FAISS? Speaking about efficiency, it does its job. I'm sure that with proper usage and fine-tuning, FAISS should be very efficient, so I will give it 3 stars as well. Speaking about effort, the initial integration is very easy. However, taking into consideration that you might need an additional database to store the metadata, and also for big indexes you might need to care about storing the index, the effort seems to be intermediate. I would give it 2 stars. Speaking about cost, it's an open source package. That is, it should be less expensive than a managed paid service. However, your instance needs to have a quite high RAM too, as this is an in-memory database, and also hosting that additional database for storing metadata may cost additional money. So I'd rate cost as intermediate as well. Okay, let's look at the third vector database in this comparison, and this will be pgvector. pgvector is actually an extension for the well-known PostgreSQL database. It's an open source extension which adds the new column type vector and allows searching by vectors. Let's look through this notebook. So first, we need to create an environment variables file and set several environment variables there. namely we need an OpenAI API key and organization name. We need a pgvector connection string, that is a string to connect to a PostgreSQL database, the name of the table, a similarity search limit, which in our case will be 0.1, and top k is the maximum number of records returned. There are multiple options how you can get a PostgreSQL database. For example, you can run this notebook locally in Docker and run a PostgreSQL in another Docker container, or you can use some online service. In this project, I used Supabase. It's a very convenient service which also has a free tier. And here I've created a project. We'll go to the project settings. And here we get that string. Okay, so we've set our environment variables. Let's run this cell. Next, we have several test messages. In this cell, we will install the OpenAI package and instantiate the OpenAI client. We will confirm that we were able to interact with OpenAI API by listing the models. Next, we will install the packages needed to interact with our database. Next, this cell will establish a connection and create a cursor. Next, so at the moment I do not have any tables here. Let's try if we are able to create a table. So this cell will create some test table, which will be called customers, and add three rows with some random values there. So it was run. Let's check what we have here. We see the table customers, and it has those test values. Okay, we need to install the pgvector extension. This can be done using this cell, or this can be done using the UI of Supabase. So we can go to databases, extensions, and here is that extension. So you just switch this toggle on. Next, we will create our table, which will be called dry. That is, it will have columns ID, text, metadata column with all the message object, and this embeddings column of type vector, and dimensionality, which are specific to the model which we will be using, and this value. So let's create our table. Let's check it. And here we see the table dry, and at the moment it is empty. Let's try inserting some data there. So here are some functions we will be using. Get embeddings vector is generating an embeddings vector using OpenAI API. Get vector ID generates an ID for a row in the table. Find record by vector ID. It's a helper function to select a row by ID. Save vector plus meta. This function will be inserting values into our table. That is, it will be saving a row which has a vector ID, text, embeddings, and the metadata. Also, in case if some message was updated, that is, it has the same ID but its text and thus embeddings changed, we will overwrite those values. Some other helper function to count rows, to delete a row by ID. And now for 3 test messages, let's add them to the table. We will generate embeddings and save the vector plus meta to the table. Logs say that embeddings were generated for the vector with such ID, and the vector was added to the database. Let's check if this is true. Right. Let's check how many rows do we have. it says that we have 3 rows. That's true. Then the function getTopRelevantMessages. It is searching for similar messages using the cosine distance. Other types of search are available, and then we are filtering. We actually can search and filter by distance. However, in this function we will be doing that manually to log all the matches and then to filter them. That is, we will print all the matched rows and then we will filter rows by the limit which we've set. Let's check what values we have. So similarity search limit 0.1, and let's test our similarity search on these 3 test messages. So, and we see that our function returned 3 records. That's all we have at the moment. And the top one has the similarity score value of 0.06. That is, this message is very close by its meaning. And though you might not know Ukrainian, you may see that there are similar words here, and these strings are really close by their meaning. Some other tests, these messages are not relevant enough. Then we have this function called getSimilar and store. So as in our pet project, we need to both search for similar messages and store them. The following function, getSimilar and store, will be generating a vector, then it will search for similar messages, and then it will store this new message and embeddings into the database. And finally, we have this list of different messages copied from a random Telegram chat. There are 91 of them, and we will generate message objects for each of these strings, and then for each of these 88 messages we will run the function getSimilar and store. That is, look for similar messages and store each message to the database. Let's uncomment this log to see the matches found, if such, and let's run this cycle. So, and we see that some matches were found. We also can confirm that our database got new messages. So let's look at our comparison. In case of pgvector, speaking about efficiency, I would also give 3 stars to pgvector. In context of this project, it seems to be doing what it needs to. And for a more detailed comparison, probably separate video would be needed. Speaking about effort, so the integration is more complex than in case of Pinecone. However, if you're familiar with SQL queries, then it should not be much more complex. It's something between 1 and 2 stars, let it be 2. In terms of cost, quite possibly that you already may have a PostgreSQL database in the architecture of your service. So it should not, in this case, it should not increase the expenses too much. However, if we would need to spin up a new database, we would probably use some managed PostgreSQL database like from Google Cloud or AWS. And in this case, for the purpose of this project, I would try something like this, T3 small or T3 medium, which would cost around $20 to around $40 a month, which is close to 1/3 or less, around 1/2 of the cost for Pinecone. That is, for me, it would be between 1 and 2 stars, and let's say it's 1. I hope that this video will be helpful for you. Please find the links to the Google Colabs in the video description.